Our first presentation is on Ownly, which is an application we've built at UCLA, kind of like broadly designed. The design has been contributed by pretty much everyone in the NDN team at this point. But so we'll be introducing what the application is, what it does, how it works. And this will be presented by me, Shinyu, and Tianyan together. And also for discussions, we are hoping that we can kind of eat our own dog food, and we can use this platform for discussions for NDNCon today. And so I don't know if it's been stand up, but we'll send out a link that you can use to join and join a workspace, a common workspace for all of us, which is something like Slack. And that can be used for discussions and editing documents and stuff like that. And you should get that. Please use the same email that you use for Eventbrite to sign up to Ownly when you get that link. When you get that email. So starting with what is Ownly? It's a fully decentralized collaborative workspace, which is built over NDN. And so the security is done with the name-based security primitives, essentially naming, trust schema, and the communication is also built on NDN primitives like sync. It can be end-to-end encrypted, and the focus here, importantly, is on end-user usability. So to make it like a real application that each one of us can use without doing 10 different things, without understanding how it works, because your common user doesn't want to understand how it works. As long as it's secure, it's fine. And so you can go to that link. It's ownly.org, which is the deployed web application. And it runs completely in your browser, so you can kind of just open it and it's good to go. That's kind of, again, focusing on the end user usability part. So what can you do? So right now, as I mentioned, there are two things. The first is discussions. You can have channels, and you can have, it's like a chat room, multiple chat rooms, and you can discuss different things in these channels. And the second is it can do collaborative editing, something like what Google Docs can do. Multiple people can edit the same documents. You can have like folder structure with documents in it, and you can upload stuff, that kind of thing. Mainly collaboration on these documents. So how is it different then from like the existing applications, which can also do this? So the first thing is that it's decentralized. There is no central point of control, especially not a third party. And the workspace owner, whoever's created a workspace, they own the data inside that workspace, and they have full control over their data because they own it. And the second thing is that it runs on all of the infrastructure that it needs is open source, is permissively licensed. And so anyone can actually run this, all of the infrastructure, and the application itself is also open source, of course. It's local first, so it doesn't need a central controller. It doesn't require a central storage server, and it can work in a truly peer-to-peer fashion. And especially the security in particular is peer-to-peer, that you don't have a central gatekeeper which tells you what you can do and what you cannot do. The workspace owner, again, controls everything. But again, they don't need to run their own infrastructure to do this. And it's secured with this name-based access control, with the trust schema, and the data can be end-to-end encrypted. All of this essentially is enabled by naming, which is NDN. So when we started building this, with building Ownly, the philosophy was that we want to build a real decentralized application. By the way, let emails send. Perfect, thank you. And so, so the philosophies here are it should be data-centric, and applications should handle only data instead of dealing with these TCP channels and like figuring out which server to talk to and all of that. The application only deals with what it needs, which is data. And so part of that is securing the data directly and to eliminate these gatekeepers, like this authentication server that sits in front of all of our data in the cloud, which kind of it's a gatekeeper to see who you let in and who you don't. And it should be peer-to-peer so that it does not have dependency on central servers, which again is part of all of this. The second philosophy is that we want to implement a generalized set of libraries which are generally usable. So we do want this application to work, but we want to have these libraries which you can use to build other applications. And so Ownly itself is implemented using in Go, using the NDN standard library. There's a talk on this later as well. And we also have an earlier implementation of the same concepts in TypeScript using the NDN TS library. And so we have these two different applications now, which use two different libraries, and we're building these libraries as we go on with building the app. And again, the focus is on usability and user experience, and essentially we're trying to minimize the human costs. Like we don't want users to have to run 10 different pieces of software to get this thing running and actually use it. And so that actually helps the end user be able to benefit from what NDN can do.
Okay. So now let me introduce the data-centric application with NDN. So in this, only the publishers, or in all applications in the end, the publisher just publishes data, which is named and has a signature with each pieces. And we just make, the application just make one data available. So that after the data is available, the consumer just need to fetch the desired data by its name. It doesn't matter how the consumer gets the data. As long as the consumer gets its data, it can validate the individual data packets, and also, so the problem reduces to synchronize the set of data among all parties by sync. And it really doesn't matter how the communication goes. You can go through some local communication like Ethernet or Wi-Fi. You can also run NDN over TCP terminals, or even run it through the HTTP or WebSocket. Like what we are doing in Ownly, we use the WebSocket overlay, or some pigeons, if you like. So the figure looks like this. For some producer in the workspace, for example, Alice, when Alice try to write something in the document of this Ownly application, later we will show you how it actually works. When Alice wants to make something, he publish his changes as an encrypted data packet, named after the Alice name. So it's like /app/Alice/data/sequence number. And also the data is signed by Alice's own key. So for all other users of this workspace, the only thing they need to do is get this data to sync, and later he can verify that the data content is properly signed by Alice's key, so he knows that this data is really published by Alice, and then he decrypt the content and put it into Workspace. So the architecture of Ownly looks like this. When someone wants to join the Workspace, he generates his Alice identity by Alice email address or DNS name. We communicate through some auto-band channel, verify that, and then generate a user identity and also a key in this workspace. And then the workspace owner can convert the Alice user identity into a workspace-specific identity. That is what Alice is going to use in this workspace app. It also goes with Alice key that is used to sign his data. And then when Alice wants to make some change to a document or send a message in the chat room, the changes that Alice makes will go through what we call the CRDT algorithm, which captures these changes and computes the difference between the documents and wrap them up into data. So Alice generated this data, that is the workspace name /UCLA/Alice with the sequence number, and sign it. And then this data goes through some synchronization algorithm that's called the state vector sync. This state vector sync propagates this data to all other peers like Bob and other workspace users. And these changes go through NDN network, and the NDN network can be built through any community. So if people want to look at the implementation, we also have a figure for the implementation architecture. But now let me introduce how the CRDT works. This is how the magic happens. So imagine we have a document look like this, and me, Xinyu, who wants to make some change to this document. Then actually this document, it shows on screen as a single document, but behind the document we have a sequence of changes. Like some of changes like made by me, some are made by Tianyuan. All these are actual data. These data differences
stored into the CRDT, and the CRDT algorithm make up this document based on all these changes. So we have mature algorithms and implementations for CRDT, and it will achieve eventual consistency. So later, suppose that I write something, I add some text into a document. So here, the CRDT will capture, algorithm will capture this change and extract new data. That is, it says that I insert some text at some position. And then I have a workspace key. Let's say it's /owner/workspace/in-u. So I will use my key to sign this CRDT change and make it into an NDN packet. That is, we have the data named after my name and with a sequence number, and it's signed by my key. And I store this data into the browser storage for my local use, and then I publish it through the SVS. And later, when Tianyuan, another user in this workspace, receives the change from the SVS, then it's going to fetch my data, and later it will verify that this data is signed by me using my signature, and then Tianyuan also saves this piece of data in his browser so he can use it offline. And also, he gives this data to CRDT. And then the CRDT algorithm will compute this new document. You can see that it looks exactly at what I see on my screen. The Ownly is implemented in two parts, the TypeScript running in the browser and also the Go, which works, the Go part, which does the networking stuff. It also runs in the browser on the WebAssembly. So after all, every stuff is running inside your browser. You don't need to install anything. The browser supports the functionalities that need to run all the NDN apps. So like we use browser storage to store the document and all the changes and data packets. And also we use the WebSocket to communicate to the NDN Workspace, to communicate with the NDN Testbed as connectivity for now. But in future, we are also exploring other connectivity, like if we want to do quick, or if we want to use WebRTC to do some real peer-to-peer communication.
The previous class we have talked about the basic application design and what magic can happen on the application layer, but we haven't gone through how these things happen on the network side, because of course we are here limited the networking part. So we know the basic philosophy of NDN is that you have named entity with transformations in between, and network just making them produce and consume data. So that means user have a name, and we merely just use DNS names and names derived from DNS as our basic tool to name things. And think about, as an application, we need to secure our communication. We secure our communication by using data-centric security. That is, every piece of data is directly encrypted and secure, directly signed. Then after we generate or produce those data, we need to have a way to synchronize the name of the newly produced data, so each consumer can fetch it on the network. And after you fetch it, this is a decentralized application. That means everyone has the data locally. That means we have to have a way to store the data in local user browser and be available for others to fetch. So the three basic things here of our design is security, sync, and store, the three S. For usernames, we assume the workspace initiator controls, say, a domain name. Then we can, if the initiator controls the domain name, it can further delegate a subdomain name to represent the workspace name. For example, we can delegate a subdomain name under name.net to be our NDN workspace name. And for each user, the reality is that the email address is the de facto user identity on the current internet. So we have no other good choice. We have to pick email. But to some extent, email itself is also some kind of email-ish thing. For example, your gmail.com, so alice@gmail.com. That's also a global unique name in the DNS namespace. That is your name in Ownly. And if you have workspace name and the username, you can name your data under your name, say if your number 8 added in the Ownly Workspace would be the NDN name data.net, NDN comp 2025 with your username gmail.com @Alice with the data, then six number be this name uniquely identified and added in the whole workspace. And the whole point of doing this is about if we can generate or use some naming convention to structure our data, it can help our forwarding and security. We will talk about that very soon. So given we secure data directly by setting them, then you need verification. For verification, the question goes back to how you verify, how you authenticate the key. After all the crypto verification must terminate at a particular point. Usually we refer that point as a trust anchor, which is a self-signed certificate. And for each user identity, the trust anchor can issue certificates to say gmail.com/@Alice. Here's a certificate for this, and the user further use this user certificate to sign the data Alice that produced. With naming convention, we can define security policies based on name matching. That is, this gmail.com@Alice can produce this piece of data. So you cannot impersonate others in networks because we only workspace owner can publish security policies that everyone must enforce. But to get all those components, you need to be bootstrapped into the system. Just like similar to IP bootstrapping, that you get IP address, subject mask, default gateway, and optionally being as local resolver. In NDN, you get the trust anchor certificate and the schema test trust policy from bootstrapping, because we know NDN is about named entities with trust relations produce and consume secure named data. So that means whenever new entity joins the system, say if you are only user, you join the system, you must have those kind of things. That is to enable you to produce data and enable you to consume the received data. If we talk in very technical specific things, for Ownly, you have to the trust anchor of a specific workspace instance is bundled together with the application itself. So we kind of out of band install the trust anchor, and because users they already have the identity, say email address, then we reuse that so-called external identity for identifying you in the workspace instance. Then the network that we use, the NDN Testbed network, verify that external identity and issue a certificate for you. So this time you have name, certificate, then you have trust policies obtained from the bootstrapping. You can enforce the security policies on who can produce what. Our authentication server, not the authentication server, but our authentication service deployed on our experimental network, testbed network, merely is verify your email by doing email challenge. And actually, if you don't get the email challenge, please check your spam box. Then the so-called certificate authority will verify whether you control the email address. If you do control it, it will issue certificates for you. But note that to this time point, the so-called NDN certificate authority, it does not control your identity. It merely verify your identity ownership and issue a certificate for you. You control the key. You control the key to produce data, and you control the data itself, because data is stored locally. As we talk about how we use naming convention to enforce schema test trust policies, we can use domain-specific language called networksec, saying if user certificate has name following, say this is the owner prefix, and we have workspace name, then this user certificate must be signed by the workspace owner or initiator certificate. Then we can enforce policy saying, okay, a particular data on a workspace project can only be signed by the same user.
So Tianan talked about Tianan talked about the trust policies that we have in the application, and so this networksec gets compiled and bundled into the compiled application at compile time, and so that is the static part of the trust policy. And now the trust policies of the application are not necessarily all static. For example, they may change at runtime. Like if I just invited a user to a workspace, like we just did for all of you, and then that means that it's creating a rule that allows the invited user to publish under the owner's namespace. It is the owner's workspace, so it's the owner's namespace, and now we let the invitee publish under that namespace. And so the idea here is that we can have these dynamic security policies and essentially break up the schema into smaller pieces, and these can be generated at runtime instead of at compile time. The schema itself, this piece of the schema itself is a signed NDN data packet, so it kind of self-certifies that the owner essentially generates this rule saying that you can publish under my namespace, and then it sends it out to the invitee. And now whenever the invitee, who is a producer of data, produces some data that needs this piece of schema to verify that data, it will attach that piece of schema to that data itself. And so then in the end, the data still describes how it can be verified, which is a combination of this cross schema, which is the dynamic rule, and the key locator. Together, they describe how to verify this data. And so that is how invitations work in Ownly, that they are policies, they are policy rules. And this new rule, whenever you invite someone, you make a rule allowing that user to publish data in that workspace. And there are two different designs here. Ownly takes the first design where users self-certify their own workspace identity. So you have identity, which is your email, and then you have a separate identity, which is only for that application, which is scoped to that application. So that application can't do just anything that it wants in your namespace. And so the scoped identity, so in the first design, the owner, your user identity self-certifies the scoped identity, and the cross schema is attached to the identity certificate, which says that you can do that. The second design is that the owner directly certifies your identity and directly bootstraps you into the workspace, which is to say that the owner issues you a certificate for a given key directly, and that requires some extra infrastructure, but then that eliminates the identity verifier itself from the chain of certificates that are used to verify that data. So there's some trade-offs in these two designs. Right now, Ownly takes the first approach, but actually the older workspace implementation did the second one, which is you directly certify the users that join the workspace. And yeah, this is just a diagram of what I just said. The owner, Bob, creates workspace, which is in Bob's namespace /Bob/workspace. Bob invites Alice to join this workspace and publish data under Bob's namespace. So then the invitee Alice will create a workspace certificate under Bob's namespace, and to be able to do that, to let others be able to verify that Alice is allowed to do this, you'll have the blue invitation data, which essentially says that Bob allows Alice to produce data under this particular namespace, which is under Bob's namespace. And this in turn is signed by Bob, saying that this is legit. The cross schema itself is legit. And so together, when you get the white data that Alice produced, you first trace it back to Alice's workspace certificate, and then you use both of these pieces together to verify that Alice is allowed to produce a certificate. And then that in turn is signed by Alice's identity key. So that kind of completes the verification chain for a third person who is verifying this data. The other thing for security is confidentiality. How do we encrypt data inside the workspace? So right now, what we take a simpler approach right now, which is have a single group key that encrypts all the data in the workspace. And there are two shared secrets. So there is a pre-shared key, which is shared with the invitation link. So if you notice that there was no PSK in the invitation link right now, is because this thing is disabled. It's kind of still in the pipeline right now, but most of the implementation is there. So the pre-shared key will be shared with the invitation link, and there is a dynamic second shared secret which is managed within the group. Essentially, when you bootstrap into the workspace, you will ask the group for this second shared secret. They will verify your identity, and then they will share that secret with you. And then that secret can also change over time, which is the key rotation. And the pre-shared key remains the same always. And so any member can respond to this request for the dynamic shared part of the shared secret. And so that means that you just need someone to come online at some point, then they will share it with you. This design, again, means that there is no central controller. it is end-to-end encrypted. You don't depend on any one point which kind of does the gatekeeping, any kind of access manager, which will decide who gets the key and who doesn't get the key. The whole key management for encryption is also handled within the group and without dependency on a third party. So coming to like outside security now to the transport part. So for transport, we use NDN sync, in particular state vector sync. And the question is, how do you notify users of a new change? Like if I make an edit or if I send a message to the chat, how does everyone know about this change? And so for that, we use state vector sync. Essentially, it's every producer keeps a sequence number. Whenever you produce new data, you increment the sequence number, and then you synchronize these sequence numbers between all of the participants in that group, which is the workspace. And that is done by multicasting the sync interest. And the example here is actually a screenshot from a real workspace that we're using. And it's essentially just the interest which carries a piece of signed data in it that gets multicast to everyone in the group, and that piece of data is secured in itself, and that has all the state vector entries, which are essentially tuples of name of the producer and the sequence number that is associated with them. And one point here, you can notice one producer can have multiple sequence numbers, as is the case here in the first one. And that is because you might have like two different devices, which are both your identity. And then you just have two different sequence numbers for both devices. And all of this together forms the state of this workspace, or the state of the sync group, which is what you see in your application. And by the way, this gets exchanged. Oh, I have a slide on that later for testbed. This gets exchanged over the NDN testbed. So, and on top of this, so we don't want like applications to just use the sequence numbers and all of that. So we have the SVS PubSub API, which is basically a high-level API to synchronize data over using SVS. And the way it works is you have a common group. The name of the workspace that you just got in the invitation link, that is actually the name of the SVS PubSub group. And the second name here is your name, which is derived from your email address. Essentially, when you bootstrap, your email address was converted into an NDN name, and that is the second argument in the SVS-PS constructor. And that starts up the group, and now you can publish data to that group, which has the data itself has a name, and it is just a blob of binary data as far as the transport is concerned. This is the application data. And on the subscriber side, so we subscribe in this application, we subscribe to all of the producers because we care about what everyone produces, but you can be more selective than that. But essentially, you give it a prefix of the producers that you want to subscribe to, or prefix of the data that you want to subscribe to, and then you'll get a callback whenever there is new data that you are interested in. And so for this application, we do need ordering, some kind of ordering, and we do need consistency. And so SVS PubSub also takes care of that. It will give you all of the data you need in order for each member. And the key thing here is that it will handle all of these things: security, segmentation internally. So applications don't have to worry about that. You give it a piece of data, it will figure out how to sign it as long as you give it the right policies. And it will do all the segmentation to break it up into packets, and you don't have to worry about that. And there's also the snapshot thing, which is to say, how do you actually prevent, like whenever someone joins the workspace, there is a lot of data produced before they join, and then you need some way to kind of compact that so that you can get it fast and bootstrap fast into the workspace. That is a snapshot part. That is also part of SVS PubSub. One other question is, do we have a sync group? And so what is the granularity? How many sync groups do we have per application? And the trade-off is that you have more groups, you have more overhead, if you have less groups, then you might end up fetching information that you don't need, which is the granularity question. And so for Workspace, for example, you might see, if you're in the workspace, that there is a thing called project at the top, and you can have multiple different projects with different sets of files. And the granularity that we chose for this application is that each project is a separate sync group, and there is one sync group for the entire workspace, like for the other parts, like metadata management, membership management, and the chat. And this is a very application-specific question: how many sync group you have, and again, there is a trade-off between them. So finally, how do we store data? Like, how do you persist data for long-term availability. And so for that, we use repo, and there's a repo running on Testbed right now, which actually persists all the data in the workspace that you are using. And this repo functions in a transparent way. Whenever someone produces data, it has joined the sync group, and then it will just fetch all the data. Yeah, so the application doesn't actually see the repo. It just fetches all the data for making it available. So finally, how do we deploy Ownly? How are you actually using it? The page that you're on is actually completely static. It's a static page. It does not have it's on a GitHub pages equivalent. And so the connectivity is done using the NDN Testbed. The testbed itself is just a network. It does not have any control power. And we use the NDN Testbed, NDN cert instance for certifying your identity, which is your first step. Finally, what is the future work or the ongoing work is, one is, as I mentioned, completing the encryption implementation. Part of it is implementing key rotations in the dynamic shared parts, looking at different ways to do this. And we also need to build the way to how you verify data after the certificates expire, because you might produce some data, your certificates have a lifetime, eventually those certificates expire, but if someone now joins the workspace, they do need to fetch that old data and be able to verify it to actually have those old files. And so this is part of the future work. And the third is that we need to make snapshots more efficient, be able to roll back changes, make bootstrapping faster, make it more efficient in terms of how much data you store. And also there is the one thing I didn't put is revocation of membership is another thing that is part of the future work. This is the last one. Yeah, and again, I hope that everyone does try out Ownly, and if you run into issues, please report them to us. The whole application is open source. There's a link in the application itself to the repo, so we welcome contributions. Thank you.
So, Varun, there are already a bunch of questions and discussions on Zoom chat and also on this workspace. I just there's a quick question about, can someone share a document with a subgroup of the users, not all of them?
Not right now. So right now there's the access control granularity is on the entire workspace. So you're either in the workspace or you're out of the workspace. But this is actually something we talked about, that we can do it progressively. We can make it further more granular. Like we can put access control on each project. Then you can sort of make a subgroup that has access to one project. And yeah, it's a question of how much you want to do in the application. So I think the project is kind of intended to be that level of granularity.